Hi, I'm Mr. Walker, and this is the 2017 Level 1 Science Mechanics paper. Before you watch this video, you'd probably benefit from having tried the paper yourself first, and I'd recommend that you do that if you haven't already. I'll put the link in below the video. So in question 1, we're looking at a situation between two riders and their horses competing in a race. We're asked to compare the speed and acceleration of Danny and Sam in the first 60 seconds. So the first 60 seconds takes us up to this point here. And just looking at the graph, we can see that both of the riders start from stationary. And Sam has a steeper line here, indicating a higher rate of acceleration, and that acceleration is taking Sam from 0 meters per second to 8 meters per second over a time of 10 seconds. So each little box representing 5 seconds, because there's 4 boxes between 0 and 20. Sam then maintains a constant speed of 8 meters per second for the remaining time, and that means that there's no acceleration. By comparison, Danny has a less steep line indicating a lower rate of acceleration, and that acceleration takes Danny from 0 meters per second to 7 meters per second over a time of 20 seconds. Danny's acceleration then drops to 0, and Danny maintains a constant speed of 7 meters per second for the remainder of that 60 seconds. So, just reiterating that, Sam accelerates at a constant rate to 8 meters per second in 10 seconds and maintains that speed. The calculation you would use is change in velocity over change in time. That's 8 divided by 10, giving us 0.8 meters per second squared. Double check your units are squared for acceleration. Danny accelerates at the constant rate to only 7 meters per second and takes 20 seconds to do so. So our calculation for acceleration is change in velocity of 7 divided by a change in time of 20 seconds, giving us 0.35 meters per second squared. Sam has a higher acceleration and maintains a higher speed than Danny in the first 60 seconds. And so that's our summary statement there for that question. Okay, so for part B, Sam's horse accelerates for the first 10 seconds of the race and covers a distance of 40 meters. Sam and his horse have a total mass of 308 kilograms. Use the acceleration to calculate the work that Sam and his horse have done in the first 40 meters. So if we use the guess method and we write down what we've been given and what our unknown is, then our given values are time of 10 seconds, a distance of 40 meters, and a mass of 308 kilograms. We need to work out an acceleration because the work done is force times distance, and in order to work out the unbalanced force on Sam and their horse, we need the acceleration. We know the mass, we don't know the acceleration, we need the force, but we can work out the acceleration from the change in velocity over the change in time. Now the change in velocity, as we saw earlier, was 8 and the change in time was 10, and so that gives us an acceleration of 0.8 meters per second squared. It's important to point out here that a lot of mistakes are made by using the average velocity formula here and assuming that's the final velocity. So the average velocity formula is distance divided by time, and you might end up doing 40 divided by 10, giving you 4 meters per second. It's important to point out that that is only the average velocity and not the final velocity, and so the final velocity is 8. You can take that from the graph, or you can double the average velocity to get that, and then divide by 10 to get the acceleration. So these are the values that are going to be useful to us. The acceleration and the mass are going to allow us to work out the force, and then the force times distance will give us the work done. So F equals ma, that's 308 mass times 0.8 acceleration, gives us 246.4 newtons. That's the unbalanced force. And then using the unbalanced force, because we're ignoring any frictional force here, that's the force we use to work out the energy, or the work done, and that comes out at being 9,856 joules. Part C. Explain the effect on work and power if a new heavier jockey was on Sam's horse, which had the same speed and acceleration over the race. Now for this one we're going to use equations for work and power, and we're going to talk through what's happening with each of the terms in those equations and use that to support our answer. So using force equals mass times acceleration, we're told that it's a heavier jockey, so mass increases, and the speed and acceleration we're told are the same, so we can state that acceleration remains constant. In that situation, acceleration is constant, mass increases, therefore using this equation here, the force must increase. If the force increases, just using the same calculation we had before, if the force increases, distance remains the same, then the work done must increase. So we've answered half of the question now. Now the other formula that we're going to use in the front of the booklet is power equals work done divided by time, and as we found out from here, the work done has increased, so over here we can say the work done has increased. The speed and acceleration over the race are the same, and so the time remains constant, and if the number on top of a fraction, the numerator, increases and this one stays the same, then the power must also increase. Okay, on to part D. So after 90 seconds, Sam and his horse have travelled 710 metres. How much further had they travelled compared to Danny and her horse at this stage in the race? Okay, so we're looking at 90 seconds here, and so just following this line up, and we know the distance travelled by Sam and his horse. We're trying to work out then the distance travelled by Danny and her horse, so that we can compare the two values. Because we're dealing with a speed time graph, the way that we work out distance travelled is using the area under the graph. So I'm just going to zoom in on that chart now. This will allow us to focus a little bit more closely on the areas we're interested in. Danny was the blue line, and so we can split up this into some shapes. A triangle here, a rectangle, another rectangle up to the 90, and a triangle up here. So I'll show you that. The first triangle has an area of half base times height. So the blue triangle is half times 20 times 7, giving us 70 metres. The rectangle here, the green rectangle, has a base, if you like, of 60 minus 20, so it's important to recognise that that's 40 there. A common mistake would be to make it 60, but the shape doesn't extend all the way back to 0, only to the 20. So 60 minus 20 times 7 gives us 280. Dividing this larger shape up here into a triangle and a rectangle gives us this grey triangle, which has an area again of half base times height. So that's 90 minus 60 times 7 to 12, so that's 12 minus 7, which is 5, and that gives us 75 metres. This final rectangle then is a height of 7 and a base of 30, 90 minus 60, giving us a total distance travelled of 635 metres. If we subtract 635 from 710, that gives us the difference between the two distances, and so that's our comparison. So Sam and his horse have travelled 75 metres further than Danny and her horse after 90 seconds. In question 2 we're dealing with lightweight Walker armour. I've put a little picture of a smaller version than we're dealing with in the question up here, just so you've got an idea of what that might look like. It's got a mass of 9.90 kilograms. What's the difference between mass and weight? Mass is the amount of matter in an object. Basically that comes from the atoms that make it up, and the weight is the interaction of that mass in a gravitational field and the resulting force from that. And then we're asked to do a calculation. So mass measures the amount of matter in an object, in this case the Walker armour. Weight is the force exerted by a gravitational field. And our calculation, using the guess method, we write down what we've got, what we don't know, identify an equation, force equals mass times gravitational field strength. I've put in a little W here, that's how I like to write my weight force, so the force weight is the W. And that equals 9.90 times 10, giving us 99 newtons. Okay, so in part B, we're asked to calculate the pressure exerted by the Walker armour on the water. So we're assuming that the hulls are rectangular in shape, one with a length of 6.55 meters and a width of 0.4 meters, and the extra little part is 4 meters in length with 0.15 width or depth. So we need to work out the area first, and then we're going to use the area with the weight that we previously calculated to find the pressure of the Walker armour on the water. So our first area is 0.4 times 6.55, and our second area is 4 times 0.15. We add those together to give us 3.22 meters squared. Okay, so using that area and the previously calculated weight force of 99 newtons allows us to substitute into the equation for pressure. Pressure equals weight force divided by area, and the weight force is 99, the area is 3.22, and that comes out at 31 pascals. You don't really need to worry about significant figures at level 1, but I've put that in there just to show what I would have rounded it to. And that's based on the smallest number of significant figures in the data that was given. Okay, so part C, the Walker armour sinks further into the water when a 67 kilogram paddler sits in it, and the only pictures I could find for free use were these ones, so apologies if they don't quite fit what's going on. Explain why the Walker armour sinks further into the water when the paddler sits in it. Use calculations to support your answer. So we've been given the mass of the paddler, so we'll be able to work out a new weight force and a new pressure based on that as part of our answer. So the weight force is mass times gravitational field strength. So the weight force this time is a combination of those two masses times by 10, which gives us 770 newtons. And referring back to our formula for pressure, since the pressure equals force divided by area and force is larger while the area remains constant, pressure must increase. It's important to state the variables that remain the same. That's often part of a requirement for excellence in these explanation answers. So make sure that you talk through each term in the equation in order to get full credit. So in this case, the new force of 770 divided by the same area of 3.22 gives us 240 pascals, and this causes the Walker armour to sink further into the water. On to question 3. We've got a crane that's lifting a container 30 meters in 15 seconds. The weight of the container is 60,000 newtons. Calculate the work done by the crane in lifting the container 30 meters. So the work done is energy. You've effectively got two equations that you might use here. Work done equals force times distance, and potential energy or gravitational potential energy equals mass times gravitational field strength times height. The fact that the weight is already done for us means that we don't need to work out mg. That's already given us force, and so either of those equations are effectively the same thing. So the weight force 60,000 newtons, the distance 30 meters, and the unknown work done. Substitute that into our equation for work done, gives us 1,800,000 joules. Remembering that work done and energy are the same thing. In part 2 we have to calculate the power of the crane, and so the equation that you've got for power, the front of the booklet, is energy or work done divided by time. So we use the work done from part 1 and we divide that by the time of 15 seconds. So that gives us 1,800,000 divided by 15 comes out at 120,000 watts or joules per second. So when the container is just hanging in the air without moving, what work is being done? If a force is being applied but it's not being applied over any distance, then according to the formula work done, there's no work done equals force times distance. There's no work being done because the distance is not changing. And so using that formula, if d equals 0, then the value for work done must also be 0. Okay, and in part C we've got the force diagram below. Explain the link between the vertical net force acting on the container and the type of motion produced while the container is being lowered. So we've got to describe what is meant by net force and explain the link between the direction of the vertical net force and motion. So the first bullet point, and I'd always recommend that you tick off each bullet point as you do it, just to make sure you're keeping track of what's been done and you're checking that you haven't missed anything at the end. The net force is the remaining force when opposing forces have been accounted for. So we might use words like resultant force or the overall. So if the large arrow represented 20 newtons and the smaller arrow represented 8 newtons, then our net force would be 12 newtons, 20 minus 8. So in this case the larger downwards force is opposed by a smaller upwards force, and that means that the net force is downwards. And bringing that unbalanced force into linking it with motion, an unbalanced force produces acceleration in the direction of the unbalanced force. That's Newton's second law of motion. And so that acceleration will be downwards as the container is being lowered. So the container will accelerate downwards as it's being lowered. Alright, final question. The crane was lifting another container and the cable broke. It was a 6,500 kilogram container and it fell 15 meters to the ground. The container had 970,000 joules of kinetic energy just before it hit the ground. We've got to calculate the energy the container had before the cable broke, and then explain why there is a difference in the energy from when it was hanging to immediately before it hit the ground. So we're going to be using the gravitational potential energy formula, EP equals mgh, to work out the energy before the cable broke. We're going to compare that to the value that we've been given for kinetic energy, and we're going to explain why there's a difference. So using the guess method, we write down the values that we've been given. I should have written out the value that we didn't know there as well, but that was EP. So EP equals mgh, which gives us 975,000 joules. so that was before the cable broke. We can see that after the cable broke and just before the container hit the ground, the kinetic energy was 970,000, and so the difference, 975,000 minus 970,000, gives us a difference of 5,000 joules. Those 5,000 joules need to be accounted for, and that's what the explain is. And so when an object's falling, there's a loss of gravitational potential energy through friction with the air, and that might be released as sound energy or thermal energy. So what I've written here is there's less energy just before the container hits the ground because some of the gravitational potential energy was converted to sound and some was converted to thermal energy through friction because of air resistance. The remainder was converted to kinetic energy, and with these sorts of questions I find it's always useful to refer back to the law of conservation of energy, and so that would tell us that the sum of the kinetic, thermal and sound energy would equal the gravitational potential energy. Okay, I hope that's been useful for you. If you've got any questions, feel free to post them below.